Hello students, today we're going to cover section 6.6, trapezoids and kites. By the end of this lesson, you should be able to use the properties of trapezoid and kites. Before we get started, we should talk about some vocabulary. A trapezoid is a special quadrilateral that has exactly one pair of parallel sides. The parallel sides of the trapezoid are called its bases, and the two non-parallel sides of a trapezoid are called its legs. The two angles that share a base of a trapezoid are called base angles. A trapezoid has two pairs of such angles. And there's a special type of trapezoid called an isosceles trapezoid, where the legs are congruent. Our first theorem discusses this special type of trapezoid, an isosceles trapezoid. And it states that if a quadrilateral is an isosceles trapezoid, then each pair of base angles is congruent. Because of the previous theorem, we can see that since QP and RS are the parallel sides of this isosceles trapezoid, angle Q must be congruent to angle P, and angle R must be congruent to angle S. So here we'll mark our diagram, Q congruent to P, and R congruent to S. Because of that, we can see that angle S must also measure 106 degrees. There are several ways to solve for the measure of Q and P. One such way is to use the fact that since QP and RS are parallel, angle Q and angle R are same side interior angles and are thus supplementary. Being that angle Q and angle R are supplementary, and have to add up to 180 degrees, and the measure of angle R is 106 degrees, the remainder, or 74 degrees, would have to go to Q. And since angle P is congruent to angle Q, we know that it is also 74 degrees. A quick way to check our answer would be to confirm that the four angles do add up to 360 degrees, which in this case they do. Problem number 2 states that the second ring of the paper fan shown consists of 20 congruent isosceles trapezoids that appear to form circles. What are the measures of the base angles of those trapezoids? The first thing that I would do in order to solve a problem like this is recreate only the portion of the picture that I'm worried about. So in this case, I've recreated the isosceles triangle and isosceles trapezoid. So I'll renumber angle number 1, and I'll relabel Y and X. One of the important things has to do with the fact that there are 20 such congruent isosceles trapezoids. The fact that there's 20 of them and the entire circle has to add up to 360 degrees means we can take the 360 and divide by 20. 360 divided by 20 is 18. So we know that the measure of angle 1 equals 18 degrees. Since this triangle is an isosceles triangle, we can take 180 degrees, subtract the 18 that we know. We have a result of 162, so 180 minus 18 is 162. If we divide the 162 by the two congruent base angles of the triangle itself, we find that each base angle is 81. So each of these two angles is 81 degrees. And by using the same side interior angles relationship again, we can take 180 and subtract 81 to find that both of these angles must be 99 degrees. Our second theorem, dealing with isosceles trapezoids, state that their diagonals must be congruent. Much like we had mid-segments of triangles, we also have mid-segments of a trapezoid. The mid-segment of a trapezoid is the segment that joins the midpoints of its legs. So we have a theorem that states that if a quadrilateral is a trapezoid, then the midsegment must be parallel to the bases, and that the length of the midsegment is half the sum of the lengths of the bases. We'll be able to prove this theorem once we get into coordinate geometry later in this chapter. The next question asks us to solve the algebraic relationship created by the midsegment of a trapezoid. In this case, we're asked to find the value of x and the length of segment MN. Now, based on the previous theorem, we know that the length of the midsegment has to be half the length of the sum of the two bases. So let's go ahead and establish that relationship algebraically. We know that the length of the midsegment, or 2x plus 11, has to equal half the length of the sum of the two bases, so half of 10 plus 8x minus 12. In this case, since these numbers are all even numbers, 10, 8, and 12, I would go ahead and distribute the 1/2. So here we have 2x plus 11 equals half of 10, which is 5, plus half of 8x, which is 4x, plus half of negative 12, which is negative 6. If we combine like terms on the right-hand side of this equation, we get 2x plus 11 equals 5 minus 6 is negative 1 plus 4x. If we subtract 2x from both sides of this equation, we get 11 equals negative 1 plus 2x. Adding 1 to both sides, we get 12 equals 2x, and therefore x must equal 6. And to find the length of MN, we have to plug x equals 6 in, so we have 2 times 6 plus 11. 2 times 6 is 12. 12 plus 11 then, which gives us the length of MN, which is 23. And so we get to the definition of a kite. A kite is a quadrilateral with two pairs of consecutive sides that are congruent and no opposite sides congruent. We get to our final theorem of the day. If a quadrilateral is a kite, then its diagonals are perpendicular. So I'm going to set this proof up as a 2-column proof. So I'll have statements and reasons. The first thing that we're going to want to include in our proof is the given information. By the first piece of given information, AB is congruent to AD, we can see that A must lie on the perpendicular bisector of BD. Additionally, since CB is congruent to CD, we can say that C must also be on the perpendicular bisector of BD. Since both A and C are on the perpendicular bisector of BD, line segment AC must be the perpendicular bisector of segment BD. This causes AC to be perpendicular to BD. So once again, we're asked to find the missing angle measures in a figure. Here we can use the properties of kites in order to assist us. The previous theorem told us that the diagonals of a kite meet perpendicularly. Therefore, angle 1 must be a 90-degree angle. By the definition of a kite, we know that consecutive sides must be congruent, but opposite sides cannot be. So here we can say KL is congruent to KN, and LM is congruent to NM. Since triangle LKN is an isosceles triangle, we know that its base angles must be congruent. So this angle is congruent to this angle. Using the fact that the three angles of a triangle have to add up to 180 degrees, we can find the third angle in the triangle that's now been highlighted in orange. 180 minus 90 minus 36 gives us a result of 54. So we know that this angle is 54 degrees. Which also tells us that angle 2 is 54 degrees. We can then once again use triangle angle sum theorem to show that the measure of angle 3 here has to be 36 degrees. So here we see a concept summary that covers all of the special types of quadrilaterals that we've seen so far. Remember, any four-sided figure is a quadrilateral. Today we studied two special types of quadrilaterals. The one on the far left is a kite. It has a special relationship between its sides, however, none of its sides are parallel. If a quadrilateral has one pair of parallel sides, it's known as a trapezoid. And in the event that its legs are congruent, it's a special type of trapezoid called an isosceles trapezoid. Previously, we'd studied quadrilaterals where both pairs of opposite sides are parallel. They are special quadrilaterals known as parallelograms. There are two special types of parallelograms, rectangles and rhombuses. And in the event that a quadrilateral is both a rectangle and a rhombus, it's known as a square. That concludes this lesson on section 6.6, trapezoids and kites. You now know the special properties of both trapezoids and kites. Don't forget to take the quiz, and I'll see you all soon.